Hello and welcome to our lesson on systems of linear inequalities with some applications. So when we're graphing a linear inequality, it's much like graphing a line with some subtle differences. And just so you can understand where we're coming from here, I want to show you when we graph an equation or a linear function like y equals x plus 1, for example. Hopefully we remember some shortcuts, like the slope of this line is 1 and the y-intercept is also 1. But to graph any function, if we weren't sure, we could make a table of values where we pick some values for x, let's say -2, -1, 0, 1, 2, or fewer is fine, whatever. But when we plug in these x values, so when I plug in an x value of -2 plus 1 means that y has to equal 1. What we end up with this point in our table at -2, -1 is a solution to this equation. A solution because when I plug -2 and 1 in for my x and y, I end up with a true statement. So -1 equal to -2 plus 1 is true. Right? That's exactly what happens when you have a solution. So when you continue to fill out this table of values, you end up with a bunch of solutions, and all of those solutions make up the graph of that line. So -2, -1, -1, 0, 0, 1, and you end up with the infinite connection of points for that line being the solutions, all of the infinite solutions to that equation. Okay? Now if we were to change this to, let's say just y is or let's say y is greater than or equal to x plus 1. Well, we still have the y equals part, which means the line itself will look exactly the same. But now, not only will the points on the line be solutions, all the points, because it's greater than, above that line will be solutions as well. For instance, if I pick a point that's clearly in this area that I've shaded, a point like, let's say, -10, 10, if I was to plug that in, -10 and 10, we'd have 10 greater than or equal to a -10 plus 1. Well, 10 is definitely greater than or equal to 9, which is again -9, which is again a true statement. So all the points above that line would be solutions, not just the points on the line. And so what we do is we shade, like I did here, to say that all the points on and above that line are going to be solutions. Now, if we make this, now I've made a big mess. If I was to take away the equal, how would it change? So if it were just y is greater than x plus 1, then this connection of points, so -2, -1, -1, 0, 0, 1, and so on, we're no longer equal to. That means the points on the line are no longer solutions. So we would represent this line with a dotted or dashed line. So that's sort of a boundary for the solution region. But the points on the line are no longer solutions. If I plug in -2 and -1, I have -1 greater than -1, which is a false statement. So again, we're going to make a dotted or dashed line to say the points on that line are not solutions anymore. But if we're greater, then the points above are still going to be plugged in to make true statements. So what we're doing when we're graphing linear inequalities is distinguishing between when we can and can't be equal to the line or be on the line. So we're going to have a dotted or a solid line, depending on if we have the equal to at the inequality or not. And then the points on the line, being solutions or not, is part of the process. We also need to decide if the points above or below that line are part of the solution region. And it's pretty simple. If we have a greater than symbol, we're going to shade above because the points above the line will be solutions. If we have a less than symbol, we'll shade below because the points below the line or less than are going to be parts of that solution region. So we are going to graph our line, and I'm going to go ahead and use m and b, the slope and y-intercept, if it's in that slope-intercept form. And again, that's just going to be our m and b. If we wanted to also just use x and y intercepts, if it's in standard form, then we can graph that way. But you can also make a table. And remember, if you're graphing a line, 2 points will be enough for you to make that table. But hopefully we have enough information by looking at these inequalities to make our graph. So the thing we got to be careful with is if we're going to use, whether or not we're going to use a solid line or a dotted line, a dashed line. So we're going to use a solid line if our inequality still has the equal to. So if we have a greater than, equal to, or a less than, equal to, it'll be a solid line. We're going to use a dashed or a dotted line if the equal to goes away. So if it's just a greater than or just a less than. And then we're also going to have to shade. We're going to shade above shade above our line if we have a greater than or a greater than equal to. And we're going to shade below our line if we have a less than or less than equal to. And again, the shaded region is showing all the points that would make the inequality true, so we call that the solution region. So graphing is the only way to show the solution region for a linear inequality. It's the only way to capture all of the points. And if you're going to graph a system, which is sort of the goal for this module, is to look at systems, then you're going to be graphing more than one at a time. So the solution region for your system is going to be where the individual solution regions overlap. So where the shading overlaps. And I'll show you with an example. Okay, so here we have y less than x plus 1. So the slope for this line would be 1. It's the number in front of x. The y-intercept for this line is also 1. So I would start with a point on the y-axis. I'm going to begin on the y-axis at 1. And then if my slope is 1 or 1 over 1, I can rise 1, run 1, make another point. And then I can really make as many as I want. And if this was an equation, I would just connect those points. But since this is an inequality, I need to decide if I'm making a dotted or solid line. So if this does not have an equal to, which it does not, this is going to be a dotted or a dashed line. So I'm going to make a dashed line through these points. And if you just wanted to make more points, that would be fine. And then we're going to shade either above or below. And in this case, we have a less than symbol. Less than means shade below. So we're going to shade here because all of the points below that line are points we could plug in to make a true statement into that inequality. And if you weren't sure, just pick one and check real quick. So 0, 0, is clearly in the solution region that I've shaded. If I plug in 0, 0, I end up with 0 being less than 1, which is a true statement. Just verify that I've shaded in the right spot. Okay, so let's try that again here. Now this one's in standard form. I would probably find intercepts being that it's in standard form. So if I put a 0 in for x, then this part would go away. And all I'd have to do is divide by 3 to see that the y value that corresponds would have to be 2. And if I put a 0 in for y, then this term would go away. And then I would divide by 2 to see that the corresponding x value is going to be 3. So I'm going to cross the y-axis at 2. I'm going to cross the x-axis at 3. Now this inequality has the equal to, which means I'm going to connect these points with a solid line. And I tried. Let's try one more time. That's close enough. Okay, so we got our line, and then because this is a greater than symbol, that greater than symbol tells me to shade above that line. So all the points on that line and all the points above that line I could plug into that inequality to make a true statement. Now this time notice that 0, 0 is not in my solution region, which means if I was to plug in 0, 0, I should end up with a false statement, so I'm just going to verify. So I get 0 being greater than or equal to 6, which is definitely false, so that should not have been shaded. So just a little work to check. Alright, now if we have a system, we're going to do the same thing twice, and we're going to see where our individual solution regions overlap. So this first one I'm going to graph using intercepts. If I make a little table here, put a 0 in for x, that's gone. 2 divided by 2 is going to make the y value that corresponds with it 1. And then put a 0 in for y. That goes away. The corresponding x value is going to be 2. So I can tell by looking at this one here, I'm going to cross the y-axis at 1 and the x-axis at 2. That has an equal to. So this is going to be connected here with a solid line. And because it is a less than symbol, we are going to shade below that line. And when you're doing this on your paper, don't go too crazy with the shading. I have multiple colors, so this is going to be easier for me to see what's happening now when I go to graph the next one. So on the next one, I have a slope of -1, and nothing being added after that, which means I have a y-intercept at 0. So I can start at the origin here, and then -1 means go down 1, right 1, and make another point. Or I can go in reverse here too, make a few, and eventually this is going to cross over and they're kind of running into each other. Maybe I picked a not good picture. Oops. And so let me just try to distinguish. Oops. Got ahead of myself. So this does not have the equal to, which means these points will have to be connected using a dashed line. And greater than means I would be shading above that dashed line. Okay, so now I've made a gigantic mess of my picture. But what I'm trying to establish here is the area where both of the inequalities are going to be true, or where I have solution regions that overlap here. So for instance, I can see in this picture 4 spaces. Oops, that is a gigantic highlighter. Let's see, I have this little area in here. I have this area that's going to be here. And then I have another area that's in between the 2 lines. And then I have a 4th area that's out here. So hopefully you can see how that's kind of divided into 4 spaces. Now in only one of those spaces we have both being shaded. So we want to be, we said, was below the red one, and we want it to be above the blue one. And where that happens is going to be this area in here. And that means this is going to be the solution region for the system. These are where we're going to have points that we could plug in to make both inequalities true. Now, I maybe didn't make my picture so accurate here, which is why we're going to use Desmos to do this as well. So if I show this to you in Desmos, hopefully it'll be a little clearer than the picture I made. But it does such a nice job of shading for us and graphing nice and accurately. So we're going to type in the system exactly as it gives it to us. So just like I have on my paper, it even did the same color. We got our red solid line shaded below. I'm going to put the next one in. Said that y was greater than a negative x, and there's the next one. So yeah, you can see it's a little bit clearer in the picture. I don't know how I messed up my graph there. I think I just didn't draw my lines very accurately, but there's our dashed or dotted blue line. Look, it even did the same color again. And we shaded above that one. And that little sliver in between is where both our overlapping solution regions are. And so that is what we would highlight and call our solution region. So these points in here represent the solution region, or sometimes we call it the feasible region. Okay? So there it is. Now what we're going to try to do is apply this process to an actual situation. And in an actual situation for this process to apply, not only will we have inequalities to graph to find a solution region for, but there will be some objective function that relates our 2 variables, and in the process we'll be trying to find some maximum or minimum with respect to that objective function. So I sort of have an example here without any context. What we're going to do is we're going to graph our system just like we did in that last example, and then we're going to try to find the coordinates of the vertices of our solution region. So what are the corners that are connecting that feasible region or enclosing that feasible region? And then those vertices get plugged into our objective function, and the ones that produce the maximum or minimum values represent the maximum or minimum for our situation. So that'll be to find max or min values. And this might be one of the rare cases where taking the context out sort of makes this not make sense. Sometimes word problems make things more challenging, but I think in these cases it's actually clearer. So we have some objective function. There's actually 3 variables in this function. We're just going to call the objective function f, and then it relates x and y. So 3 variables, and that is not something we're going to graph. We're not graphing in 3 dimensions here. Okay, that's not going to come into play until we try to find a maximum or minimum value. What we're going to graph is what we call our constraints. So they're called constraints for our applications because they're telling us what regions of the graph, what points, what x's and y's we're restricted to that will make all of the inequalities true. So let's graph these one at a time. And actually, I'm going to go ahead and use Desmos to graph these. So the first one we have, maybe I'll just not going back and forth. I'm going to put it in Desmos too, but I think I can graph these by hand, so I feel a little bit embarrassed trying to go to my calculator. All right, so this first one's going to cross the y-axis at -5. And be careful, I made the axis go by 2's here. And then the slope is 3. So I'm going to go up 1, 2, 3, and over 1. And that's over 2. So there's that. And I could try to do that again, but let's just sketch this out. So we're going to connect these with a solid line. And I did pretty good on that one. And this one is less than, so we're going to shade below that line. And I just don't want to go too crazy with my shading, because I'm going to have to do this 3 times in one picture. So the second one crosses the y-axis at +7, so 2, 4, 6, 7. And the slope is -3, so down 3, and right 1's going to be like right there. Again, we have an equal to, so solid line. And I missed. And I missed again. Alright, 3 times the charm. Nope, that was worse. Okay, so I'm trying to use my draw tool, but it's not working with me. So let's do that. And that was a greater than, so I want to shade above that one. And then the last one says the x values less than or equal to 6. That's going to be a vertical line. And that vertical line at 6. So that's going to be solid vertical line at 6. 2, 4, 6 is going to be here. And we can't go above or below that, but where are the x values less than 6 would be left of 6. Now I have this big mess in my picture. What I'm looking for, again, where do I have all 3 shaded? And that's going to be this triangular region in here. So this is my solution region. Now notice that solution region has vertices. So as there's these 3 corners that are enclosing. And at one of those points, we're going to get the maximum or minimum with respect to this objective function. So I need to know exactly where those points are. Now, we talked about ways to find those intersections. Those intersections would be the solutions to each of the systems. So we have an intersection here, we have an intersection here, and then we have an intersection here. Those 3 intersections would be like solving 3 systems by hand. Now that's a bit much for this one problem. So I just want to make sure my picture's right, and I don't want to do the work to find those intersections. So I am going to put it in Desmos, which I maybe could have started that way, but that's okay. So less than or equal to 3x minus 5, and y is greater than or equal to negative 3x, and then plus 7, and then lastly we have x is less than or equal to 6. Okay, now just so it corresponds, I'm going to edit these colors. So I did a red, and then I did a green, and then this one I did blue. Okay, so there it is, the same picture. And what I need are these vertices, and if I just tap on the graph in Desmos, it will tell me. So that point up there is going to be at 6 and 13. I'm going to call this one A. So A is at 6. I can't write all of a sudden. I was trying to do a parenthesis and a 6 at the same time. All right, so 6 and 13. And then I have one here at 2, 1. So I'm going to call that B. And B, again, is at 2, 1. And it looks like I actually did that pretty accurately because they look to be in about the right spot. So this is 6 and negative 11. Yeah, so that one's a little off on my paper. Oops. Let me call that C. Let's try to be consistent here. And that was 6 and negative 11, right? Let's make sure. Yeah. Okay, so now that I have those vertices are going to get plugged into our objective function. So when I plug in 6 and 13, remember this is an x value, this is a y value. So I have negative 8 times 6 plus 5 times 13. And let me just not do anything silly here. Negative 8 times 6 plus 5 times 13 is going to be a total value of 17. And then let's plug this one in. So that's going to be negative 8 times 2 plus 5 times 1. I can do that one without my calculator. That's going to give me a negative 11. And then lastly, if I plug in this one, I have negative 8 times 6 and 5 times a negative 11. So negative 48 and negative 55, that's negative 90, 103. And I just don't trust myself. So let's make sure. Oops. Okay, so negative 103. Now, when we plug these three in, 17 was the highest value that we got. So we would say we have a maximum value of 17 at the point 613. And then this was the lowest value that was output from our objective function. So we would say that we have a minimum value of negative 103 at the point 6 and negative 11. Okay, so that is the process of maximizing or minimizing an objective function with a set of constraints in inequality form. So now this is the same process we're going to be looking at in an actual word problem. So you can see where some of this is kind of useful. And when we apply this process to word problems, it is referred to as linear programming, which sounds fancy, but this is just maximizing or minimizing some objective function with constraints. So we call it linear programming. Fancy talk, not a big deal. Okay, so it says that Evelyn and Elaine are customizing cell phone cases at their kiosk in the mall. They have enough supplies to customize up to 30 large cases and 80 small cases, and they know they'll be able to sell at least 10 large cases and 60 small cases. However, they won't have enough time to customize more than 100 cases total. If they profit $6 for each large case and $4 for each small case, what is their maximum profit? So the objective function comes from what they are trying to maximize or minimize, or in any case, what is trying to be maximized or minimized. In this case, they're trying to maximize profit. So my objective function comes from the profit. And in this case, we'll call that profit P. The profit is $6 for every large case and $4 for every small case. Well, I don't know how many large cases or small cases there are going to be, so we're going to have to introduce our variables in here as well. So I'm going to call the large cases x, and I'm going to call the small cases y, although if you flip that, it doesn't matter. So it says they profit $6 for every large case, so $6 for every x, plus $4 for every small case for $4 for every y. So there's our objective function. Now that one's just going to sit on the back burner. We have some constraints. Even though, they're trying to maximize their profit, there's a limit to what they can do. So we've got to go back and write inequalities for all of these constraints. So first it says they have enough supplies to customize up to 30 large cases. Up to 30 large cases. That means the number of large cases can't go over 30. It has to be less than or equal to 30. And then it says they have enough supplies to customize up to 80 small. That means the number of small cases can't be more than 80. It's got to be less than or equal to 80. And they know they're going to be able to sell, it says, at least 10 large cases, so that the x's have to be, oh, I meant to change colors. I thought I did. They're going to sell at least 10 large, so the number of x's was largest is going to be greater than or equal to 10. And also, what do we have here? At least 60 small. So the number of y's has to be greater than or equal to 60. And finally here, I need another color. Let's go to custom. How about an orange? Okay, it says they won't have enough time to customize more than 80 cases total. That means the number of x's and y's together, the number of smalls and larges, the number of cases total, can't be over 100. So it has to be less than or equal to 100. All right? So those are the constraints that are in the problem. Now notice, we're going to have to graph those to find the feasible regions, the only way to find the solution to a system of inequalities. Notice that the graph is limited to the first quadrant. So there are some unstated constraints, right? The number of cases, x's and y's, small or large, whatever it is, can't be negative. So everything's in quadrant 1. So they're unstated constraints. The x's have to be greater than or equal to 0, and so do the y's. So we're going to be in quadrant 1. So we said x's were the large cases. So I'm going to put large cases over here. Let's be large. And then the y's were small cases. So I'm going to put small cases this way. Okay, so let's graph these constraints. So first, it said that the x's had to be less than or equal to 30. So that's a vertical line at 30, and these are all going to be solid. They all have equal to's. So we're going to be 30, and then less than that, actually don't have to go beyond the axis here, less than that would be left of that. So I'm just going to put a couple little arrows here to tell me to shade that way. Since I'm going to be graphing so many, I want to be really careful with my shading. Okay, now that it said that the x's had to also be greater than 10. So we're between 10 and 30. So 10 is going to be another solid line here, and greater than that. So we're in between those two lines for right now. And then it said the y's had to be bigger than 60 but less than 80. So less than 80, there's 80. We're going to be below that. And then greater than 60. So we're going to be above that. And that was really sloppy. Let me try that again. Okay, apparently I can't draw a line this way. Alright, so greater than 60, less than 80. So right now we're in that little square, but there's one last constraint. The last constraint says that the number of cases total has to be less than or equal to 100. So if I was to graph this, I would find the intercepts. If you put a 0 for x, y is going to be 100. And if you put a 0 for y, x is going to be 100. So it's going to cross both axes at 100. So 100 here and 100 here. And then let's play connect the dots. Let's see if I got it. Alright, not too bad. And we have to be less than that. And so we have to shade below that. Oops, draw tools on. Below that line. So if we're between, like in that little square, we're between these two, and between the two horizontal, between the two vertical, and below that orange line, I can see my feasible region, my solution region, is going to be here. So this is the number of cases, small and large, that can be made where all of the constraints are met, where they're making at least 10 but less than 30 larges, and at least 60 but less than 80 smalls, and the number of total cases is less than or equal to 100. So all the constraints are met. Now we have to figure out in that solution region of all those points where are we actually going to maximize the profit, and that maximum is going to be produced by one of those vertices. So we have 6 vertices in here, looks like. So I'm going to just label these A, B, C, D. Oh, there's 5 of them. I can count, I promise. So those 5 points, one of those 5 points is going to maximize or minimize my profit. So let me figure out exactly where those are, and I could do work to figure that out. Actually, some of those are pretty easy, right? Like A, I can see, is at an x value of 10 and a y value of 80. So A is going to be at 10 and 80. And B, I can see has an x value of 10 and a y value of 60. So 10 and 60. And then C, it's not as clear. Or maybe it is. My graph looks pretty good there. But I know that the x or the y value at C is going to be 80 because it's part of that pink line. So if I know that y is 80, and I have to find the x that goes with it, it looks like it's going to be 20, and it happens to be because it's where it meets that particular line. So we're looking at 80 and 20. Although if you put this in Desmos, it would give you those points as well. So that was 20 for x and 80 for y. And go back to black. So 20 for x, 80 for y. And this point here at D has an x value of 30. I can see it's on the green, and that means the y value has to be 70, and that looks pretty accurate. So that's 30 for x and 70 for y. And then E is at 30 and 60. So those ones are pretty easy for me to see. Again, if you wanted to just put it in Desmos and tap on those intersections, you're going to see the same picture and it would tell you all of those points. All right, now I need to plug them all into my objective function to see which one gives me the maximum. So the profit is going to be 6 times x plus 4 times y. So here, if I plug in, my profit will be 6 times x plus 4 times y. In this case, we've got 60 and 320, which is going to make 380. And then here, 6 times 10 and 4 times 60, clearly going to be less. So that was going to be 60 and 240, which will make 300 the profit. And then here, 6 times 20, 4 times 80 is going to be 120 and 320, so 440 for our profit. That's the best so far. And then here, 6 times 30 and 4 times 70. That's going to be 180 and 280, so 3, 4, 60. And then finally here, 6 times 30 and 4 times 60, clearly going to be less than the last one we just did. So 180 and 240, which is 420. That is the largest right there. So there's going to be a max profit of, in this case, $460 when x is 30 and y is 70. So when 30 large and 70 small cases are customized, produced, whatever the language was that was used in this particular problem. Okay? So you're graphing, which Desmos could do for you. You're finding the vertices, which Desmos could do for you. And then you're plugging those vertices into your objective function to find your max, or there will be some cases where you're looking for a min, but it would be the same process, just look for the lowest. The hard part's up here. Okay, make sure when you're writing your objective function that it is for the item in the problem that you are trying to maximize or minimize. So again, here it said what is the maximum profit. That told me that my objective function had to be written for that profit. And then be careful writing those constraints. Okay? So I think we should be good. Should have enough to get going on your practice. But as always, if you need some extra help, just reach out. Till next time, take care.